of this. Okay. So as a reminder, today the extra credit is due, and Keyshawn, your exam, and Sam, is your exam, and Andrew. Okay. So the extra credit's due. If you, it's due by 3. I'm in my office from noon until 3, so you can bring it by any time. And I strongly encourage you to do that to make sure you're getting back as many points as possible. Okay. So what I want to talk about now, and really what a lot of today is using the new thing we learned, implicit differentiation, to actually get some new regular derivative rules. And so the end result is largely, we're going to see some new derivative rules. But rather than just saying, here's what they are, we can see or actually come up with them ourselves, which is sort of interesting seeing where they come from, but also justifies a little bit why implicit differentiation is worth learning about. Rather than just a way to ask new questions, it really helps us with our kind of main thread. So the first new kind of function that I want to talk about are inverse trig functions. So we'll eventually see all of them, but at least for the development, we'll focus on y equals inverse sine of x. So one thing to keep straight is in this case of a -1, this means inverse, it's not a power. So when we've seen things like sine squared, that was actually sine and you're squaring that thing. In this case, it is not 1 over sine, it means inverse. Another notation that you can use, and either one is fine, I'll often use inverse sine, is arc sine is another notation that means the inverse of the sine function. And as a brief recap of what this actually means is that if sine inverse of x equals y, that means that x is sine of y and y, let me write it like this, and negative pi over 2 is less than or equal to y is less than or equal to pi over 2. So what sine does is it takes in an angle and it spits out a number between -1 and 1. What the inverse function does is that it takes in a number between -1 and 1 and outputs which angle produces the number x that you picked. And among the angles that work, you have to pick the one from negative pi over 2 to pi over 2. So for instance, if we look at an example, if we wanted inverse sine of 1/2, the number we're looking for here is we're looking for the y, so sine of y equals 1/2 and y comes from this interval negative pi over 2 to pi over 2. So that's what you're actually doing. And if you look for that, it can be helpful to pull up the unit circle, which is something like this. These numbers, negative pi over 2 to pi over 2, is this right half. So we're looking at this part of the unit circle, from negative pi over 2 up to pi over 2. And we're looking for which angle could you pick in that range that has a sine of negative of 1/2. And actually, that turns out to be pi over 6. And you do need to be careful here, because another angle whose sine is 1/2 is 5 pi over 6. 5 pi over 6 is another solution to this equation. But why that isn't sine inverse of 1/2 is that it's not in the right range. And pi over 6 is the one solution which is in that half of the circle. Another weird kind of thing with inverse trig functions is often when you think about inverse functions, it's that when you compose them, you put one inside the other, they cancel each other out. But that doesn't exactly work with inverse trig functions. So if we look at this number, sine inverse of sine of 3 pi over 2. At first glance, your instincts say sine inverse and sine, those cancel each other out, and we just get the 3 pi over 2. But that's not exactly what's going to happen, because this 3 pi over 2 is not in this range. 3 pi over 2 isn't a valid number to come out of inverse sine. The only numbers that can come out of an inverse sine have to be between here. So the way that we understand this is really say, well, sine of pi over 2, that, if we put that here, that's at the bottom of the unit circle, 3 pi over 2. And so sine of 3 pi over 2 is -1. So now we want to know which angle in the right range has a sine of -1, and that's this angle negative pi over 2, which is at the same point, but is off by like a rotation. So this is negative pi over 2. So they're canceling in the sense that they're getting to the same spot in the unit circle, but the angle is different. And so that is the fastest possible review of inverse trig functions. What we want to ask is, how do we find the derivative of something like this? So if we want to find the derivative of this, the way we can do it is, rather than thinking of this version, y equals sine inverse of x, and so we want to find y prime for this, instead, look at this version where we've moved sine to the other side of the equation here. So instead, look at sine of y equals x. So here, it looks strange because we have sine of y, but if we think about it in terms of implicit differentiation, this is an equation that has x's and y's in it, and we know how to differentiate everything in here. So we'll do implicit differentiation with this equation. And that'll give us y prime for the thing we actually care about. So if we do implicit differentiation, remembering how that works, here on the left, we have a y, which means first take a normal derivative. Sine becomes cosine. But then, because it's a y and not an x, we get an extra factor of y prime. And then on the right, we have x, and the derivative of that is just 1. And there are no y's, so we don't have to do anything different. And then, as implicit differentiation goes, solve this equation for y prime. So that means divide both sides by cosine. So y prime is 1 over cosine of y. Which is the derivative, but isn't the form that we want. We started with our function y as a function of x. We would like the derivative to also be a function of x. So we're not quite done yet. But what we can do is notice the following facts. Well, first, we have the Pythagorean identity, which is sine squared plus cosine squared is 1. Sine squared y plus cosine squared y equals 1. Solve this equation for y, not for y, but for cosine of y. So that means subtract the sine over and take a square root. So we get that cosine of y is plus or minus, because we're square rooting a square, the square root of 1 minus sine squared of y. So that's close to, that's telling, the reason we're heading that direction is we have cosine of y on the bottom. We want to know what we can replace that with. And we can't do it yet because of this plus minus, but the observation that lets us pick, is it the plus or the minus, is that for y in the range where we're looking, so we're only looking at y variables between negative pi over 2 and pi over 2, which is this right half of the unit circle. And over here, cosine is always positive. On the unit circle, cosine is the x coordinate, and on the right half of the circle, the x coordinate is positive. So what that means is that when we were trying to solve for cosine, cosine is supposed to be positive, so we should take the positive one. So what we get is that y prime is equal to 1 over the square root of 1 minus sine squared of y, which kind of seems like we just made it worse. But we really didn't when we look at this line up here. Sine of y, that was equal to the variable x. So instead of sine squared y, we can put x in. And now we get the form of the derivative that we want. We get that y prime equals 1 over the square root of 1 minus x squared. And that is the big takeaway right here. That's our new derivative rule. It's surprising that we go from inverse trig function to something with no trig at all. But the derivative of inverse sine is 1 over the square root of 1 minus x squared. Okay. Questions about obtaining this derivative formula, in particular the implicit differentiation, which is the new thing that we're using. Some of the other trig I'm less worried about. Okay. So the big takeaway is new derivative rule, inverse sine is 1 over the square root of 1 minus x squared. Okay. So there are other trig functions for inverse cosine and tangent and the rest that if you wanted to, you could similarly figure out where the derivatives are by using this type of work. Once is enough, so I'll just tell you what those derivatives are. So we have inverse sine. If we want the derivative of inverse cosine, this is really close to this derivative. This is -1 over the square root of 1 minus x squared. Then we have tangent inverse. Its derivative is 1 over 1 plus x squared. The derivative of cotangent inverse is, again, off by a minus sign, -1 over 1 plus x squared. Then there's the derivative of secant inverse, which is 1 over x times the square root of x squared minus 1. And then lastly, the derivative of cosecant inverse is the negative of that, -1 over x times the square root of x squared minus 1. Okay. So we have all these derivatives. We can find them in a similar way, but to put you at ease a little bit, to be totally honest, the only 3 of these that I will ever use in any problem, quiz, homework, exam are the basic ones: cosine, tangent, and sine. These 3, I'm putting them up for completeness just so you see their derivatives. They do have derivatives, they have formulas you could look up, but as far as what to try to commit to memory, don't worry about them. They're there, but I'm just not going to use them. So these new inverse trig derivatives come from implicit differentiation, but from another kind of perspective, they're just more derivative rules. We'll add them to the rest and use them whenever appropriate when we're taking derivatives. So for instance, we could say, find the derivative for y equals inverse tangent of x to the minus 1. So in here, one thing to keep straight is the minus 1s there. While they are notationally identical, they are very different in what they're representing. The minus 1, when it's attached to a trig function, is inverse. So that function is this guy right here, and we have its derivative. X to the minus 1, on the other hand, is a power, and so that's x to the -1 is 1 over x. So that's its reciprocal. So although they look the same, they're really interpreted in different ways. So if we want to find this derivative, then looking at it, it's the chain rule, the outer inverse tangent, and we've got that derivative here. The inside function is x to the minus 1, and that's a power rule problem. So if we find this derivative, inverse tangent, the chain rule says becomes 1 over 1 plus something squared, and that something instead of x is what was inside here. And you can leave that as x to the -1. I'll write it as 1 over x, just because I'm going to do a little simplifying afterwards because it's sort of surprising. But then we have the derivative of the inside, which if we use the power rule, says the minus comes down, we subtract 1 to get the new exponent, -1 minus another 1 is -2. And if we simplify this, it actually simplifies to be pretty nice. In this first fraction, square the top and bottom of this 1 over x to get 1 over 1 plus 1 over x squared. Then instead of a negative exponent, rewrite this as a fraction too. So it's -1 over x squared. And if we multiply these across, so the top is -1 times 1. The bottom, if you multiply x squared through here, becomes -1. X squared times 1 is just x squared. X squared times 1 over x squared. All the x's cancel, and you just get 1. So what is surprising here is that this function, inverse tangent of 1 over x, turns out to have the same derivative as inverse cotangent. And I kind of say this every time, and maybe I should eventually figure it out, but there's not some shorter direct route to get there. So what we can see here is that these two functions I'm going to write down, the one we have here is tangent inverse of 1 over x and cotangent inverse of just x. These two functions have the same derivative. And it almost seems like there's some algebra that could get you from one to the other, where here we flipped the inside from x to 1 over x. Cotangent is 1 over tangent, but the algebra doesn't actually work directly. It's just sort of some sort of coincidence. But is kind of weird, and I think this is an interesting example to do, so I keep it. Okay. Questions about finding this derivative? So in a similar manner to how we found the derivative of inverse trig functions, there's another kind of inverse function that we can find the derivative of. And this is derivatives of logarithms. So if we have y equals log base a of x, what this means, how you know that log base a of x equals a number y, is that saying the same thing as a to the y equals x. So the way that I need to think about logarithms, because they're not an especially natural function to understand, is that log base a of x is the exponent of a that gives you x. So when you write this down, the number that it's equal to is what power of a gives you the number x for different choices of x. So for instance, something like log base 10 of 10,000, that is what power of 10 gets you 10,000. And because there's 1, 2, 3, 4 zeros, 10,000 is 10 to the 4th. So that's what this number is. Or for instance, if we have log base 4 of 8, this number, what power of 4 gives you 8? And this is not as straightforward to see, but this number turns out to be 3/2. And you can check that this is true because 4 to the 3/2 says take the square root of 4 and then cube it. And the square root of 4 is 2, 2 cubed is 8. So 3/2 is the power to go from 4 to 8. A special kind of logarithm that we've encountered, but now we're really seeing what its derivative is the natural log of x is defined to be the log with base e. And so if we write something like the natural log of e to the 4th, or let me do this, the natural log of 1 over e squared, this is saying what power of e are we writing in here? And this is -2, because you could rewrite this as e to the -2nd power, rather than in the bottom of a fraction. So that is, again, a super quick review of what logarithms are. But also, like before, this is what they are, but how do we find their derivatives? We can do this using the implicit differentiation method, which we used for inverse sine. It's a little cleaner in this case. We don't have to worry about the trig identity or the range or anything, but we can still follow the general path. So if we want to find the derivative of log base a of x, so any logarithm, and the natural log will be a special case of this. So we want to find the derivative of y equals log base a of x. Like before, replace that with this other equivalent equation. But if we replace y is log base a of x with a to the y equals x, in this form, we know how to take the derivative of everything. A to the y, we've talked about exponential functions before. So if we do implicit differentiation on this, well, the derivative of exponential functions is you get that function back. So we get a to the y. But we also get the natural log of the base. So we get a natural log of a factor. But then we also, because there's a y there, not an x, get a y prime factor. And on the right side, x becomes just 1. So not a lot going on there. And then solve this equation for y prime. So divide by that other stuff. Y prime is 1 over a to the y times the natural log of a. So that is the derivative. That's a formula for the derivative, but we want it to be in terms of x. And what we can do is a to the y is equal x. So replace that a to the y in our derivative with just the variable x. Those things were equal in our kind of translation among all of these variables. And so this is our derivative rule. What is the derivative of log base a of x? It is 1 over x times the natural log of a. questions about getting that? Or I guess I sort of skipped over the log summary, but questions about any of this logarithm material? So to collect a couple pieces of information, we have this new derivative rule, and it's a rule that this is where it comes from, but also we can use it whenever appropriate. So we have our derivative rule that the derivative of log base a of x is 1 over x times the natural log of a. A special case is, what is the derivative of the natural log of x? So the natural log of x is base e, so that means when we take its derivative using this general formula, we get 1 over x times the natural log of e. But the natural log of e is 1. So we get just 1 over x, or x to the minus 1, if you want to write it like that. And at this point, actually, if you stop and think about it, 1 over x hasn't been the derivative of anything so far. Like, it's a pretty simple function, but it's just never been the derivative of anything. And the reason why is, well, because we haven't talked about the natural log yet. But especially in this form, x to the minus 1, it's a power of x, but it can't ever come out of the power rule, because the power rule subtracts 1 from the exponent. And if you were going to subtract 1 and end up with x to the minus 1, you must have started with 0. And that means you have a constant, and that derivative is 0. So this isn't something that can come out of the power rule. This is where 1 over x appears. It's also worth comparing the derivatives of the logarithm functions to the derivatives of the exponential functions. So the derivative of a to the x is a to the x times the natural log of a, and the derivative of e to the x is just e to the x. So there's a kind of parallel here where there's the simpler looking derivative, the natural log and e to the x have simple derivatives. If you change the base of the exponential function or the base of the log, you have a really similar looking derivative, but with this extra factor. And this is a big reason why the natural logarithm is called the natural logarithm. When you're told, here's this number e, we can talk about logarithms and exponentials with this base in pre-calculus, like, okay, whatever, this is a weird number, I don't know why I'm doing this. But the reason why it's natural is because from the point of calculus, that's the simple kind of basic case. And then any other number you have to adjust by something involving the natural logarithm. So if you had ever wondered why it was called a natural logarithm, this is a big reason. But beyond these derivative rules, now we can say, great, we have these rules, we can use them wherever we need to use them. So we can ask questions like this. For this function, x times the natural log of x, is its tangent line steeper at x equals 2 or x equals e? So we know before we really do anything, we're going to have to take the derivative. Once we get that derivative, we're going to have to check the derivative at 2 and e, and a line with a bigger slope is steeper. So that's what we'll actually check, but that's kind of the very last thing we'll do. It's really take the derivative and then evaluate at these 2 points. When we take the derivative, x times the natural log of x, we want to think about what rules we actually have to use. First up is the product rule, natural log of x times x. And then within the product rule, we have these 2 functions. So the natural log is going to be one of the derivatives we actually take. So writing out the product rule, that's the derivative of the first function x times just the natural log, and then flip it, just x times the derivative of the natural log. X doesn't have a power, so that becomes 1. The natural log of x, our new rule, says that becomes 1 over x. So this actually simplifies kind of nicely. We don't have to write multiplying by 1. And in the second term, x divided by x, that all cancels and we just get 1. So this is our derivative. And then what we want to do is put in these 2 values and see which one is bigger. If we put in e, then we get the natural log of e plus 1. The natural log of e simplifies to be just 1. So we get 1 plus 1, just 2. If we put in 2, then we get the natural log of 2 plus 1. And this doesn't simplify. We're kind of stuck with that if you want an exact answer. In this case, we really want to compare the numbers, so you do need to put this in a calculator and see what you get. The natural log of 2 is about 0.69. So this is 1.69. We're steeper at e because the value of the derivative is bigger. So steeper at x equals e. Questions about this problem? Okay. Let me do another problem, which is not really introducing anything new, but there are 2 ways that we'll be able to do it, and the second one suggests a new direction. So this one will be just a straight derivative problem. Let's find f prime of x for f of x equals log base 3 of the square root of x. So this problem is a chain rule problem, first of all. There's the outer logarithm, and the derivative of the logarithm is this first derivative rule right here. The inner function is the square root, and that's x to the 1/2, so that's a power rule problem. So when we take this derivative, the derivative of the outer function is 1 over x times the natural log of 3, but we don't just put x there, we take the inside square root, and that is what is put in the bottom along with this extra factor. And then we multiply the derivative of the square root, which is the power rule, which brings the 1/2 down in front. The new exponent is 1 smaller, x to the negative 1/2. So that's our derivative. And in this case, or I guess first I'll pause, questions about just getting this derivative. So in this case, it actually simplifies really nicely. So let's see what happens there. How we can do it, well, the first part we'll leave like it is, But if we write that second factor as a fraction, so the 2 is in the bottom, and also rewrite it without a negative exponent, so we put another square root in the bottom. And now that it's a fraction, we can multiply across, with the big simplifying being square root times a square root. Well, you're squaring a square root, and that becomes just x. So we actually get 1 over x times 2 natural log of 3. Or sort of however you like grouping it, it's 3 things multiplied, a 2, a natural log of 3, and an x. Which maybe you wouldn't have expected given where we started, because this looks like kind of a mess. There's another path to this derivative, which is much easier from a calculus point of view. If we pull out and remember the right pre-calculus step. So, or if f of x is log base 3 of x to the 1/2, a pre-calculus move that it's maybe been a while since you've encountered, but there were some rules for simplifying logarithms, where you could either take a complicated log and break it apart, or take a bunch of logs and combine them into one. And so there is a logarithm rule that we can use before doing the calculus. In this case, what turns out to be true is that when you have a logarithm and your inside thing is raised to a power, which is what we have, the x is being raised to a power inside our logarithm, then this is equal to the logarithm of just x, but instead of that being raised to the 1/2 power, you've multiplied by 1/2 in the front. And this is not a power rule type thing moving the exponent down. This is an algebra fact about logarithms. But if we do this, and maybe you didn't remember this, but it's a valid rule, what you can definitely say is from here, the calculus is much easier because it's not a chain rule problem. There's not even a power of the thing inside. This is like one derivative rule. Because if we differentiate this, the 1/2 is a constant. That just is brought down when we take the derivative. The log base 3 of x, that's our new derivative rule. But it's not combined with anything. It's just that single rule. So that becomes 1 over x times the natural log of 3, which is up to multiplying things together what we got before. So where we're going to start next time is I'll remind you of all of these different logarithm rules. There are 3 of them for powers and multiplication and division. And what we'll see is that there's a trade-off we can make by using some of these logarithm rules first. Makes the calculus much easier, rather than having a very complicated logarithm that you need to use the chain rule and the power rule and the quotient rule for maybe a few times. Okay, so that's where we'll wrap up. Remember, get me your extra credit by the end of, or by 3 o'clock today. Also, if you haven't picked up your exam, I recommend you come into my office and do that.